Bismillahirrahmanirrahim and Assalamu alaikum, my dear students. I welcome you to the lecture number 18 of Electric Circuit Analysis 1. Today we are going to study inductors, the performance of inductors under DC condition, and series and parallel combination of inductors. How do we sum up or reduce a network having multiple inductors while they are in series combination or either they are in parallel combination? So before moving on to for solving some problems, I would like you to please recall that under DC conditions a capacitor is replaced by an open circuit because current through the capacitor is zero, because there is no variation in the voltage, and under DC conditions an inductor is replaced by a short circuit because the current is constant, so there is no voltage across the inductor. Practice problem number 6.1 gives us a network in which a 10 ampere current source is powering an RLC circuit, and under DC conditions we have to find the voltage across the capacitor, the current passing through the inductor, and the energy stored in each of the elements, the passive element, that is the inductor and the capacitor. So first of all we'll see the circuit under DC conditions and replace by its equivalent. Under DC conditions we replace the inductor by its short circuit equivalent, the capacitor by its open circuit equivalent, and what we get is the net circuit is this. Now the voltage can be found by this, that see the capacitor, it was in parallel to the 2 ohm resistance. So as you know that parallel elements have the same voltage, so the voltage across 2 ohm would be equal to this. These two elements would have the same voltage, so the capacitor voltage can be found by finding the voltage across this 2 ohm resistance. And current IL, you can see that now the current IL that is flowing through this inductor is now flowing over here, and you can simply find that this is the current. The net circuit has been reduced to this, that we have a 10 ampere current that is powering the circuit with a 6 ohm and 2 ohm resistance in parallel. So here when we have to find the current through one branch, we have to use current divider rule, because this current is being divided into two paths, this 6 ohm path and this 2 ohm path. We have to find the current through the 2 ohm path. So by current divider rule, I2 ohm is equal to R opposite. This means R 6 ohm divided by the total resistances among which the current is being divided into or multiplied by the applied current, which is 10 ampere. So opposite resistance is 6 ohm, 6 plus 2 8, and into applied current source is 10 ampere. So by simple arithmetics we get to know that the current through the inductor is 7.5 ampere. Now we have to find the voltage across the capacitor. The voltage across the capacitor is found by, I just told you that it is equal to V2 ohm. V2 ohm is Ri, R2 ohm into IL, which is I2 ohm. So by inserting it the value of current which we just found as 7.5 ampere and the resistance value is 2 ohm, we get to know that the capacitor voltage is 15 volt. Now we have to find the energy stored in the capacitor and energy stored in the inductor. First of all, we will find the energy stored in the capacitor, which is 1 by 2 CVC square. By inserting it value of capacitor and the capacitor voltage, we get to know that the energy stored in the capacitor is 450 joules. Similarly, in inductor energy is given by 1 by 2 LIL square. By inserting it the value of L, which was 6 Henry, IL, which was found as 7.5 amperes, we get to know that the energy stored in the inductor is 168.75 joules. Moving on to the next topic, we have series and parallel inductors. The purpose of this topic is to reduce the complexity of a network when we have the inductors in a series combination or in a parallel combination. So when we have inductors, n number of inductors for example, and we have to find the equivalent inductance, what we do is we take the sum of all of the resistances in the series combination, that is the L equivalent, the equivalent inductance would be the sum of all of these inductors. However, when we have the inductors in its parallel combination, what we do is we take the L inductance, equivalent inductance is the reciprocal of the sum of the reciprocal of each of the individual inductors. So for two inductors, just like in resistors, what we do is 1 over L equivalent is 1 over L1 plus 1 over L2, which is by when we invert this equation, we get to know that LEQ is equal to L1 L2 divided by L1 plus L2. These are two parallel connected inductors. So example 6.1 give us a parallel series combination of inductors, and we have to find the equivalent inductance across these two terminals. So moving on to solve this equation, what we get to know is that these three inductances, this and this 20 Henry, 12 Henry and 10 Henry, these three are in series with each other. And you know that I just taught you that the equivalent inductance when the inductors are in series is a simple sum of all of the inductors. So it will be 20 plus 12 plus 10, which comes up to 42 Henry. Now I'll replace this by 42 Henry in the given network, and I get to know this. Now I can simply see that this 7 Henry and this 42 Henry are in parallel to each other. So we'll take the equivalent inductance of this. The equivalent inductance is by this mathematics is 6 Henry. Now replace this combination, that is these two, by the 6 Henry resultant equivalent inductance in the given circuit, and we get to know that among these two terminals, this 4 Henry, 6 Henry and 8 Henry all are in series to each other. So we'll take a sum of the all of them, and this would be the equivalent inductance among these two at these two terminals, which is 18 Henry. Moving on, practice problem number 6.1 is also a similar kind of a problem in which we have an inductive ladder network, and we have to find the total inductance or the equivalent inductance at these two terminals. We have to simplify this circuit. Similarly, you can see that at the right hand side I have these two which are in series with each other, 40 millihenry, this small m stands for milli, and 20 millihenry. These are in series with each other. I'll take a sum of them, and this comes up to be 60 millihenry. Now I replace these two by one inductance, which will be 60 millihenry. The rest of the circuit is the same. Now in order to find a relationship, to highlight the relationship, I'm using a different color pen, which is red pen. So 30 millihenry and 60 millihenry, you can see that these two are in parallel to each other. We'll take the parallel equivalent of these two inductances, which is the product divided by the sum of the two inductances. So products come up to 1800, sum is 90. We get to know that this equates to 20 millihenry. Now this new 20 millihenry is in series with this 100 millihenry. So series inductances always sum up as equivalent inductance. So 100 plus 20 is 20, and now I replace these two inductances by the equivalent, which is 120. Now you can see that in the new circuit, every time I'm making a new circuit to enhance understanding or for this topic. So now this equivalent, that is 120, is in parallel to this 40 millihenry. Now we'll take the parallel equivalent, which is the product of these two value, 40 into 120, divided by the sum of these two, which is 40 plus 120. We get to know that this comes up to 30 millihenry. Now the resultant circuit is this. I replace this combination by 30 millihenry. The circuit on the left side remains the same. Now you can see that this 20 millihenry and this 30 millihenry are in series with each other. Equivalent inductance would be a sum of these two, which will be 50 millihenry. Now finally the circuit summarizes to two inductors, 50 millihenry and 50 millihenry, in parallel to each other. I told you in resistance topic, when we are to solve two parallel resistances or two parallel inductance of equal value, their equivalent is 1/2 of the net value. If we are having 50-50, their equivalent would be 25. If we had 40-40 over here, the equivalent would have been 20. So the rule is L equivalent is 1/2 of the net value, since they are both of the same value. That's why I'm using this rule, which is 25 millihenry. In case you cannot remember this rule, please you simply use the typical formula, which is 1 over L equivalent is 1 over 50 millihenry, 1 over 50 millihenry, or alternatively L equivalent is product of these two divided by the sum of these two values, which is product is 15 to 50 is 25 millihenry, and 50 plus 50 is 100. So I get to know that by this method also the equivalent inductance is 25 millihenry. So you can see that using both the methods, if I use this method or I use a typical method, conventional method, the value of equivalent inductance is the same. You can use either. Now kindly please solve problems in exercise of chapter number 6 related to series and parallel inductors and inductors and capacitors under DC conditions. You will be asked, and in your next assessment you will be asked about these concepts. In case you have any problems, please do let me know in the question answer session. Thank you very much. Best of luck. Allah Hafiz.